What is going on, everybody, and welcome to part 14 of our Deep Learning with Python, TensorFlow, and a Neural Networks tutorial series. In this tutorial, what we're going to be talking about is the high-level abstraction layer and library on top of TensorFlow that is TFLearn. So you actually have quite a few options when it comes to abstraction layers. There's Keras, which is for TensorFlow and Theano, but then there's also TFLearn, which is what we're covering now, TFSlim, and skFlow. Okay, so we've got really four pretty popular abstraction layers on top of TensorFlow. They're all contenders, which is pretty interesting because TensorFlow is actually still in beta. So the fact that we already have this many is kind of strange, and why people keep coming out with new ones is beyond me, especially when the other ones are relatively okay. So from my looking through them, I decided to go with TFLearn. Keras was the other number 2 contender, but TFLearn makes a little more sense if you're for sure going to be working with TensorFlow. You might as well be using TFLearn because it's right on top, and so it's a lot easier to use some of the more interesting functionalities of TensorFlow with TFLearn. I'm sure Keras can be done. It's just not as simple, I don't think, at least for me. So, okay, why might you actually want to have abstraction? Why would you even want to do this? So there's like 2 major reasons. The one reason is just for simplicity's sake. So this code's actually fairly short, for making a neural network, especially like a convolutional neural network. This is actually not very much code. Okay, there's not too much here, but the code isn't super simple. It's fairly verbose, and it could be a lot simpler because really all we need to do is have a convolution layer. Actually, we need to have an input layer, convolution 1, convolution 2, and then the fully connected layer, output layer, and we're done, right? That's all we really need. So we could definitely simplify this. So that's one thing, is just simplifying the code, and kind of in line with that, but for a whole nother reason is you're a lot less error prone if you use a higher level framework that's going to just not have the availability there for you to make that error. And so TensorFlow, I don't claim to be the best programmer in the world, but it's easy, at least for me, to make mistakes. And I think it's fairly easy for anybody to make mistakes. Now, it couldn't come at a better time because I actually made a pretty important or pretty large mistake in the previous tutorial, but it went unnoticed because it didn't impact. It had a huge impact relatively, but in terms of percentage and all that, I just chalked it up to, we don't have enough data, okay? But that wasn't actually truly the answer. So let's talk about that really quickly, and then we will get back into TFLearn. So what I forgot to do, two things. One thing is the biases. In this case, it didn't actually matter. I guess this data set's good enough. It doesn't have biases, and it has no 0 inputs. So biases really don't matter that much in this example, but we should have had them. So normally it would be, x times weights plus biases, right? It's always that. So, and I keep trying to bang that into y'all's heads, but for some reason, I guess I just don't have it yet. But anyways, always input times the weights plus the biases. Don't forget that stuff. Come on, guys. So anyways, actually, I was the one that forgot it, and it was brought up pretty quickly by other people. So anyway, maybe just me. But it's an easy mistake to make. Same thing with the map mole that I made initially. Really easy mistake to make as you're just kind of going through it. And so if you're just quickly prototyping something or testing something, or even you just want to use a really simple convolutional neural network or a recurrent neural network, it's easy as you're going through to just make a pretty simple mistake. So that was mistake number 1. Mistake number 2 was we didn't have an activation function, right? We're not running the rectified linear operation here. That is what accounted for basically about 2% of accuracy, because really we just have this single activation function on the fully connected layer. Again, whoops. So anyway, to properly fix that, you would do tf.nn.relu, and just encase this entire thing. So I'm just going to copy this. Copy, paste, and encase. And that is how the convolutional neural network should look, until someone corrects me. So anyway, so that's what it should be. And let's go ahead and just run this really quickly. I'm actually going to run it in the background as we work on TFLearn, but I just want to show you the actual output, the real output that it was supposed to be. So let's just do Python 3 CNN example.py. Let's make sure it runs. And then as soon as we get one loss, I will move it aside and we'll get into TFLearn. Cool. So, moving this over, I'll show that before we run the TFLearn model. So let's make this full size. Let's make it a little bigger. And then let's do File, Save As, and we're going to save this as CNN TFLearn. Cool. And we're going to delete it all. Crazy, I know. Okay, so with TFLearn, basically you're going to use only TFLearn. You don't need to import TensorFlow. In fact, if you did import TensorFlow, it would be treated as a completely separate package, and it's going to do the whole loading the GPU libraries and all that kind of stuff. If you're on the GPU version, otherwise, I guess you wouldn't really see that, but it's redundant to import them both. In most cases, anyways. Import TFLearn. Then we're going to say from TFLearn.layers.conv, we're going to import conv_2d and maxpool2d. So these are two functions that you should already know what they do. We've already written them. I haven't looked to confirm this, but I would wager they are identical to the ones in that convolutional neural network. I think it was the MNIST for experts data tutorial on TensorFlow. I'm going to wager those are the same, but anyway, they're going to do the same thing. Also, while we're talking about this and making these imports, notice that we're importing these functions. We're not writing these functions. These functions, I hate to say they don't exist in TensorFlow, because they actually might, but I don't think they do, right? But in a higher level abstraction layer or library, they will exist, and if you're going to use an abstraction library, the goal is to write 100% of your code in that abstraction layer and not try to write custom stuff around the abstraction when you need to. Chances are, if you find yourself in a situation where you're like, I really need to do this, and you're thinking you're going to do something fancy to get around it, chances are it's already been done, and it's there, you just don't know about it. So I highly, highly, highly recommend you go to tflearn.org and go through the things here. You don't necessarily have to read everything, but what you should do is go through the examples. We'll pull up at least one example later on, because it'll be important. Hopefully I won't forget, but anyway, I might. But anyway, hopefully we'll pull up an example later. But look at the examples. You can go to the models. You've got a deep neural network and generative neural networks. Those are the two major model types here. We haven't really talked too much about generative models. Those are what interest me the most, but they have like the lowest use case right now. They're the most like kind of research intent, like they're more in research as far as application is concerned, in the spectrum of research and application. Anyway, layers. Okay, you've got core layers, convolution layers, recurrent layers, normalization layers, embedding layers, merge layers, and estimator layers. Got lots of layers here. Some of these you probably don't even know what they are. Feel free to look at them and learn more, and if you want to learn more, you can always Google these things. But we're going to be using convolution layers. Okay, then we've got operations that are built in. You've got some data management. Probably a really useful one to look at is data utils and pre-processing, and then maybe the data flow and augmentation. But those first two probably have a lot of really useful things in them that otherwise you'd be writing yourself. So think about it. Anyway, I'm going to set that aside for now, and we're going to keep importing stuff from TFLearn. But just know, if you're ever, if you want to learn more about these things, you can always go to tflearn.org, or you can just straight up Google tflearn.layers.conv2d, and you'll get to the documentation, and you can read more about what it is you're actually employing. And you really need to, otherwise you're not going to know what the heck you're doing. So next, from TFLearn, actually mostly you just want to learn what the parameters are, right? Like the function names are actually pretty good, right? You know what the function names are, but it's pretty useful to know what your options are with that function, and what your parameters are. That's just essential. Okay, so anyways, because a lot of the parameters are required. Anyway, so from tflearn.layers.core, we're going to import input data. So this will be your input layer, basically. Dropout, and then the fully connected layers. So input layer here, dropout just to have dropout, fully connected layer functionality there, convolution layer or convolution here, max pooling there. So we've got the convolution layers, fully connected layers, input, and in theory output with fully connected. So those are just all of our kind of definitions almost right out of the gate. Then from tflearn.layers.estimator, we're going to import regression, since we're going to use regression at the very end. And then finally import tflearn.datasets mnist as mnist. So that's just TFLearn's mnist. Now we're going to have x, comma, y, comma, test x, comma, test y is going to equal mnist.load. Load data. What is it? Input? Yeah, load data. My brain just wanted to turn off there. One hot equals true. Okay, so here we're just loading in our data, really nothing crazy. Now we're going to have a reshape for x. X equals x dot reshape, and the reshape we want is -1, 28 by 28 by 1. And then we actually want to do the same thing to test x. So I'm just copying and pasting test x, whoops, test x, and test x. Okay. Now, convnet is going to equal, first we've got the input layer. So input data, and the shape of that input data is none by 28 by 28 by 1. And then name here, for now, this isn't totally essential, but later on, if you want to use fancy tools that TensorFlow offers you, like TensorBoard, I'm pretty sure that's mostly why we're using name here. Also, if you, and never mind, we'll just have it there. So now what we're going to do is begin, that's our input layer. Now we have two of the kind of convolution and pooling layer. So convnet equals actually it was _2D. This takes a bunch of parameters. We're only going to use a few of them. First of all, we're going to input convnet. It's going to be, we use 32 for the size. So we use 32, window is 2, and then the activation function, just activation equals, we use rectified linear, so relu. Then what we're going to do is convnet equals, now we're going to do the pooling, max pool 2D. Again, we pass in here convnet, and then the window is 2. Okay, so we're going to take that, copy, paste, and we just do the same thing again, basically, only this one is 64, since that's what we used before, and hopefully everyone can run a network of this size. So, or most people can. So those are your two convolution layers. What's next? Fully connected layer. And then followed by what? Dropout. Okay, convnet equals, and this is fully connected. What are we going to pass? Convnet, that's the input, is whatever's coming at this point. We use 1024 for the input there, and then the activation again is relu, rectified linear. And finally, and basically, just for the record, there is a default. I think the default is just linear. Let me look. Let's see. TFLearn dot layers dot conv dot conv 2D. Let's look it up, guys. So bring it over, and we're looking for conv 2D. Where's activation? Yeah, so the default is linear, so probably not very good. All right, but you couldn't forget an activation function because it has a default. Okay, it would be nice if the default was better than linear, but okay. Moving right along, rectified linear, fully connected. Now what do we have to do? We have to drop out. So we're going to convnet equals dropout, and what are we applying dropout to? Convnet, and then what's the dropout rate? Well, we used 0.8, so we'll stick with that. Next, what we're going to do is we have the output layer. So the output layer itself is also a fully connected layer. So convnet equals fully connected, input convnet, 10 this time, and the activation function is not rectified linear, it is softmax. And let us do convnet equals, and then finally we run that regression. And in this sense, it's almost kind of a little more verbose than TensorFlow was, if you ask me. But anyway, we run regression on the convnet, and the optimizer is Atom. learning rate. I honestly don't. I think we use the default, and I think the default is 0, 0. We'll go with 0.01. That should be fine. The loss was cross entropy. In this case, that's referred to as ooh, we're running into my face. Categorical cross entropy. Hopefully we didn't typo that. Next, the name here, we're going to call this, these are the targets. So you're going to basically, in this is you're calculating the loss basically. So from the input, after all the weights and all that, how close are we to our targets? So that's the regression layer. Now we're pretty much almost done. So model equals TFLearn dot, and of the two models available to us, we've got deep neural network and generative neural network. Which one do you think it is? It's probably DNN. So we're going to do DNN. So TFLearn dot capital DNN convnet. Cool. Now, once you've done this and defined all of this, you can do all the quick commands for a model. Now, we don't have anything trained at this point, so we're going to do model.fit, and we're going to fit the following. In normal cases, you can just pass x and y, but you can also give them labels, and we're going to go ahead and do that. So we're going to say input, that's your x, your targets, that's your y. The number of epochs, even though it's an epoch, is 10. Pretty sure epoch is not one of those weird words that doesn't have like s as the plural, but okay. Someone let me know if I'm wrong. Validation set is equal to, and basically the same thing. I'm going to take this, copy, and list, paste. Rather than just x, it's test x, and then this is test y. Test y. I'm getting lost. Let's hit enter here. This was for the validation. Cool. So validation set, and then we have snapshot underscore step. We're gonna say 500. This is just how often do we want it to report to us, like what the final value for this is. You'll see exactly what I'm talking about in a moment. Show metric, we'll say equals true. And finally, run ID, we'll call this mnist. Great. One final look over, because that was running off the screen, and I think we're good. Looks good. Okay, so we fit. Now, just to throw all this all in one basket, this is the exact tutorial from before, so it's at 30 lines right now. 30 lines compared to, out of my way, seeing an example, I think it was like 80 lines, possibly? No, 73 lines. Okay. So, a little less than half, but even more importantly, like, we don't have any of this nonsense. We don't have this, like, we don't really have, like, annoying looking code. Like, this code is super clean. It's super easy to, like, look at it and be like, oh, okay, I see exactly what's happening, like, immediately, right? And people who like Python like that. So, that's pretty nice. And in a moment, I'll show you another example of a much more complex model that, yet again, is very simple like this. Whereas, like in this case, it's kind of like, you know, whether you use a for loop or not to iterate through something. For like a small neural network like what we have here, it's not as visible as to how much this is saving us. But on a much larger network, I'll show you what it looks like. And actually, I don't even have full code for the network I'll show. But anyway. So what we're going to do now is model.save, and so whenever you're done with fitting a model, you can save the model. So we'll just save this as tflearn.cnn.model. Cool. So that's our model file. Okay, and all that does is saves your weights. It doesn't save like your model. It's not like we're pickling a model or something here. It's just saving weight values. So when we load it back in, the only thing we get to not have is like these lines here. We still have to keep convnet, and later we'll load and the definition of model, and then what we do is load back in the model, because again, all this contains is just settings for your weights. That's it. There's nothing more to it. So if you try to put this on a neural network that has 3 convolutional layers and then 5 fully connected layers, it's going to be like, oh, I don't know what to do, okay, because it doesn't have the same values, okay? So you just have to make sure you're matching. But anyway, we'll save. So let's go ahead and save this and let's run it. Hopefully we don't have any issues. Let's see, Python 3 CNN TFLearn.py. View, zoom in. Okay, downloads the data and starts the training. So you can see it's got like this really nice UI almost, right? I do wish that maybe accuracy was more like maybe bold and orange or something like that. Like loss is really important, but accuracy is also important. So I'm not sure why we don't do that. And really all these values are pretty important. But like you obviously wouldn't need to capitalize atom and epic and stuff. But anyway. Not that they give a crap. They're not watching my videos. So, so anyway, we can already kind of see actually like after like the first kind of batch, it was done. But the step, remember we did that like snapshot step 500. You can see that's like here 2,000, 2,500, 3,000, 3,440, 3,500, 4,000. There's some where it doesn't honor that, like 2,500, then it does 2,580, and then it does 3,000, and it does 3,440. I don't know for sure. Maybe that's the end of the epic or something like that, and it's like, okay, we're done anyway, so here's what we have right now. Okay, I'm not positive on why it does that. That's just my guess. So while we're waiting on that, we're almost done. We're at epic 8. So I'm going to move this over. Now what we could do later is, like, once that's trained, we can just comment this out. We already have the definition of model. So now what we could do is we could say model dot load. I'm pretty sure. I don't think it's load data. I'm pretty sure it's load. We'll try load and we'll see what happens. So load TFLearn.model. So copy this, paste that. All right, and let's see if we're done yet. Yes. Here they are compared. Both about 97, 98% accurate. So one is 97.5, the other one's 97.8. If you kept rerunning them, you might get slightly different numbers. But yeah, somewhere in that range. Just wanted to show they're the same model, same thing's happening. So yeah, okay. So we've done that. Let's save this. We'll load in TFLearn, and then let's like do something. So one thing you could do is like you can predict. So you can print model.predict. Let's do test x. The firsteth test x, and let's just get a quick prediction. This index out of range. Really? Oh, weird. All right, I'm not sure how that mistake was made, but all right, test x, that. All right, let's try again. Test x1. Nope. Test, oh, I see what I did. Okay, test x, it needs to be a list. There. That was way too difficult. So what was the initial one? I can't remember how that, it was almost like part of the thing or something. I don't know. Okay. So as we can see, 0, 1, 2. So for literally the character 2, but also the second index, is a perfect 1.0. If we ran like an argmax or something on here, this would be the max val. So so that's a prediction that you could do. Also, like let's say you want, like you've trained it and then you're using it and then you've got another new batch of data. Okay, fine. Model.fit, right? Run model.fit again, and then again save it, of course. And you know, you can keep going on this way. So it's not totally, it's not like it's online in the sense that it's constantly training. But you could do something like that. Now, I'll save that. And the final thing I want to show you is going to the examples. I'm going to pull up AlexNet here. This is an example of how to apply AlexNet. So AlexNet is a network that was proposed and actually seems to be one of the most successful, if not the most successful, for image data. This is AlexNet. So as you can see, you've got like layer here and here and here and here and here and here. You got a lot. It's much more complex, and you've got this kind of divide even right here and this connections. It's a much more complex network, and yet we're able to. Whoops! I thought it was in this other tab. It's over here, I guess. Yet it was able to be applied in. This is 56 lines, but 16 of those lines are used just to source AlexNet. Okay, so really 40 lines that was applied. I don't even want to know how long it would take to write this in TensorFlow, or how many lines that would be. Not that lines are like the ultimate measure of anything, but it would definitely be pretty confusing looking as opposed to just this, right? Okay. So anyway, that's TFLearn. That's a little bit on why you might want to do abstraction. There are other modules and libraries for doing this with TensorFlow. Feel free to check them out. I felt like TFLearn was the simplest. Like, I actually liked TFLearn. I just thought if you're going to do abstraction, you might as well do it with TFLearn. Keras is a really well documented one. It's an old one, and it works with TensorFlow or Theano as the backend. So a lot of sample code that you're going to find might actually be in Keras, because Keras has been around for a really long time, as opposed to TFLearn, which has not been around for a very long time. So you're going to find less examples of models in that. But at the end of the day, TensorFlow hasn't even been around for that long anyway. TensorFlow is still in beta, so either way, you're going to have a hard time finding code even just written in TensorFlow. But for the most part, every time a new paper comes out, people implement it because they want that to be the main GitHub or whatever that gets traffic for that implementation of something in some framework or library or whatever. So people are actually pretty quick at doing it. Anyway, that's it for this tutorial. If you have questions, comments, concerns, whatever, feel free to leave them below. Otherwise, as always, thanks for watching. Thanks for all the support and subscriptions. And until next time.